So I ready? Okay. So Tim, could you start your this
Okay.
section?
Okay. So I hope my voice holds out another hour and a half. We'll see. Um, okay, welcome back after the break. I'm I'm surprised you want to hear this much from me, but I've got a whole nother talk. Um, and let's go ahead. So this has been really interesting to work on the slides for this. It gave me a chance to review my career with open source and with Linux and with Sony and all kinds of aspects. And normally at a Japan Jamboree, it's very common for me to do a status of embedded Linux. I will have a little tiny bit of that at the end, kind of where are we now. But when I get to that, I'll explain how much I'm doing. And let me start with I'm a principal software engineer at Sony Electronics. It's still me after the break. So this is what I'm going to talk about, the history of embedded systems. A lot of this is personal experiences. So I'm sure there are aspects of the embedded systems development that I'm not aware of. This is kind of my view of things. I'm going to talk about the rise of Unix, Linux, and open source. Some of the obstacles that we saw in the early days to Linux adoption and how I believe those were overcome. I'm going to talk a little bit about Moore's law and then what I consider to be the embedded open source contradiction. Um, and then a little bit about where we are now, not a lot, and then just a little recap. So let me talk about the history of embedded systems from my personal standpoint. So I don't know if these are embedded, but they were really small systems. So when I started in my career, my first programming was on a TRS-80 that had 12K of RAM. Okay, notice the K. It's 12,000 bytes of memory and a cassette tape for storage. Okay, so that should tell you how old I was, uh, and or how long ago this was, rather. My first commercial programming, I did commercial programming on an Atari 800 computer. It's an 8-bit microprocessor. It had a 6502 running at 2 megahertz, and that was unbelievably fast at the time. It had 32K of RAM and a 90K floppy drive. Okay, so uh, this was not an embedded system, but I feel like I earned my time on small systems and learning how to optimize code. My first timeshare system was on a PDP-11, and that only had 64K of RAM, and it had a whopping 11 megabytes on storage. Um, my first product, one of the first products I worked on, I was at Novell. I worked on something called NetWare Lite, which was a DOS background process. I don't know if you remember DOS, but it had these things called TSRs, terminate and stay resident programs. Um, and we were able to create a full network operating system. So DOS was a standalone uh, uh, operating system, single processing, and we had to make it multiprocessor. And we did a network operating system, which meant it handled, I think it was on the order of 50 or 60 uh, protocols for file reading and sharing and print sharing and stuff like that. We did it in 56K of memory. We thought that was pretty impressive. Um, what was even more impressive was back then the application space was limited to 640K, although the machine had 1 megabyte was the addressable RAM because it was only a 16-bit machine. Um, and but the ROM took up a good 384K usually. But we had structured our code so that each individual unit of it could fit in less than 6K, and we wandered around memory and found little holes that we could jam it into. And so most of the time, when you loaded our program, it showed the same amount of memory available as before it was loaded. So we were very proud of that. There was no impact to the 640K on that. Um, so some of the companies I worked for Novell. That was where I did NetWare Lite. Caldera, I'm sorry. Uh, if you know who that is, then you know there's a whole story there. I worked, and then from Caldera, I went to Caldera Thin Clients, which became Lineo, which was an early embedded Linux company. And then I've been at Sony, but I've been at several different business units at Sony: Sony Electronics, Sony Corporation of America, Network Entertainment, Sony Mobile, and Sony North America is where I'm at now. So my history with Linux started at Novell with something called the Corsair project. So Novell had acquired the rights to Unix, but they were also looking to build a desktop operating system. This was a popular thing to do in the 90s. And so there was a group of us inside the company that took Linux, and we had a Linux desktop operating system. Novell did not want to pursue this project. They didn't. I remember I talked to the CTO of Novell personally, and I remember the quote very clearly. He said, "Tim, the world does not need another operating system," and so they're very skeptical of this. I took some, and so I actually left that company to go to Caldera, where we continued that work. And I worked on the Caldera Open Linux desktop system, and that, in my opinion, that was a very groundbreaking system. Had a very advanced desktop, had a Netscape web browser way before web browsers were cool. This is 94. And then the real key thing that it had that other people did not have is we had compatibility for existing Unix applications and existing DOS applications. So it could run a lot of the software that was already in existence at the time as a Linux operating system. That was a big deal. I mean, we had like WordPerfect for Unix ran on our desktop. But that didn't last. I eventually left Caldera and joined Caldera Thin Clients and then Lineo, and that's where I started working with embedded Linux. Our first product was a Linux-based router. We also had a product that we could fit Linux and a browser on a single 1.5 inch, 1.5 megabyte, 3.5 inch floppy. So a single floppy, you could plug it into an existing DOS machine or actually anything because it was a bootable floppy, and you could turn that into a web-based terminal and browser and stuff. Our highest profile product was probably the Sharp Zaurus. So I don't know if you guys remember that back that far, but one of the very first early PDAs. I think it was the first PDA, personal digital assistant, to run Linux, and we ran that with Embeddix and Qt. And then I came to Sony. Lineo fell on hard times. It's a long story. But since 2003, I've been at Sony. I've worked on digital cameras, camcorders, some other products. I mostly focused on size reduction, boot time, and kernel maintenance. I did a little bit of work, not a whole lot of work, but a little bit of work on the Linux add-on for PlayStation 3. I worked on USB drivers and a little bit of cell processor support. And then I switched over to TV sets. I did some work on the Sony Internet TV, tried to boot Android faster. Android is highly resilient, highly resistant to being boot fast. Anyway, I worked on a TV crash handler. And then I switched over to mobile phones, did some Qualcomm SoC drivers and stuff like that. At the same time as kind of this internal work, Sony asked me to work on advancing Linux strategically. And my very first task at Sony, in fact, kind of the primary reason I was hired, was to help them create something called the CE Linux Forum. And I've actually been involved before and after I got employed with Sony. I was involved with other Linux consortiums. One of the reasons they hired me, I had been involved with the Embedded Linux Consortium. But the Consumer Electronics Linux Forum was really kind of an important project for Sony strategically to help Linux turn into a good embedded OS. That eventually transitioned to the Core Embedded Linux project at the Linux Foundation. And most recently, I've been involved in helping to start the Linux for Space and the Space Grade Linux initiative. So the Space Grade Linux is technically right now just a little working group, but it looks like it's on track to become a full-blown project, hopefully this year. And some of the things I did along the way is I started some conferences. So the Embedded Linux Conference was started in 2005, and that conference is actually still running. I just finished the program review last night in my hotel room. We're having a call tomorrow on the program committee for that. So, and it's actually, if you're going to Prague, we have it in October this year in Prague. I think its schedule is going to be really good. We had a huge number of proposals and some really interesting topics. So that's my little plug for ELC. Um, I worked on a project called Fuego, which is a test automation suite, and I started a conference related to that. The Automated Testing Summit ran for a couple of years, and then COVID hit, and some strange stuff happened. And then the Embedded Open Source Summit. So that's just a little quick review of personal information of mine. Let me talk about the rise of Linux, Unix, Linux, and open source. And I talked a little bit about this in the previous talk. So Unix was started in the 70s, and it started at Bell Labs, and that was free. Again, it was free because there were some legal issues going on with AT&T in the U.S. AT&T had been banned from doing any computer work, and so they had made this operating system Unix as part of their research division, and they decided to release it for free. And that kind of created the very first notions of source available software. You could get the source for Unix. You could download it. Well, eventually that forked into several different kinds of Unix. The most popular being BSD, Berkeley Software Distribution, but BSD Unix, free BSDs, Xenix was Microsoft's, AIX was IBM's. And I didn't even know it at the time. I was in high school in 1979. I don't, you can do the math. But I was actually using Unix and I didn't even know it. I was just doing BASIC on a terminal emulator on a PDP-11. And so I was just learning BASIC to learn computer science. But the system, it turns out, was actually a Unix system. So that was the 70s. By the time the 80s rolled around, there were all kinds of options for people to do hobby programming, and personal computers had become a thing. And what happened in 1991 is a college student named Linus Torvalds decided he wanted to write his own system. And he started seriously from line one, complete clean slate, from scratch programming of the Linux operating system. And it only took about 8 years, and all of a sudden it was big enough to start to being used in the industry. And embedded Linux took off in 1999, and there were companies like MontaVista, Lineo, and TimeSys. So let me talk about some of the obstacles in the early days and how we got where we are now, where embedded Linux is unquestionably the most popular and the most dominant embedded operating system on the planet. And then I also want to talk about the open source contradiction here. So I had this slide in my other talk, but this is kind of the history of open source and where the World Wide Web was created. And Linus Torvalds announced Linux in 1991, same year. I don't think it's a coincidence that those happened the same year. I think there's a synergy between the web being accessible and being created and open source starting to take off. But you see other projects like the Apache Web Server, the Mozilla project, those were important open source projects, and then Android. And then by 2008, which is still, that's a good 18 years ago, you're starting to see GitHub and just a flood of open source projects on the internet. So, but in the embedded Linux timeline starts a little bit after that. So again, start with Linus Torvalds and the World Wide Web created. And then we have the first embedded Linux vendors around 98 or 99. And then the green boxes there are some of the organizations or the forums that have been created. So ELC was created very early on. The Sharp Zaros was in like 2001, I think. Self was created. And then the very first embedded Linux conference was 2005. And then you see a couple of other of these I'm going to talk about. But I think some of the milestones was when the BeagleBoard was released and the Raspberry Pi. And then some of these other organizations like Self transitioned over to the Linux Foundation. You had automotive grade Linux. The Octo project was started and CIP was started. So what were the obstacles in those early days? Well, in 1998, no one had even heard of Linux. Okay, Linux was not the dominant operating system. People were people were running around inside their companies hiding from their management that they were running Linux. They had it on floppies, and you would find engineers who were playing around with it without letting their company know. Um, and no big companies, says no companies, that's supposed to be big. No big companies were using embedded Linux. Um, and Linux, to be honest, it was a pretty primitive system. It was not POSIX compliant yet. It lacked a lot of things. It lacked real-time support. The size was way too big compared to some of the RTOSes at the time. It was very slow to boot. It was not optimized for power management. I think power management, I don't even think was a factor. And the most important thing was it was just fundamentally missing processor support. Linux originally was developed on x86, and it was a couple of years until it got put onto strong ARM and then ARM. But the vendors, if you were a vendor of silicon, you were going to do a board support package for like Vertex or for VxWorks or PSOS. You were not going to do a board support package for Linux because it just wasn't known. Another big obstacle was the development board prices. So Linux was kind of in the hobby space. It wasn't in the commercial space yet. And so, and if you had like a custom development board, a prototype board, that could run you upwards of $20,000. It was very, very common for even an entry-level board to be $2,000. I can remember the OMAP evaluation board. I happened to get one of those, and it was $2,000. And it's like, that's just not the type of thing that a hobbyist would be able to get and play with. And so I think one of the big key things that happened was when Texas Instruments was very visionary, and they decided that they were going to actually create a low-end board that was sub 200 price point. And I can't stress enough, this was unheard of at the time. The idea that you could get a board that you could play around with yourself, put your own operating system on it. Even personal computers, right? We think of personal computers like $400,000, $2,000. Personal computers at the time, I remember I got a 286 with 16 meg of RAM, and it was $5,000. So even personal computers were very expensive. But you saw BeagleBoard kind of started this trend. TI did that, and then the Raspberry Pi Foundation also wanted to do a low-end system. The first Raspberry Pi was only $35. Amazing price point. And so this made embedded Linux really accessible to a lot more people. Some of the early embedded Linux vendors, we had Monte Vista, Lineo, which I said was an offshoot of Caldera, and TimeSys were kind of the big three at the time in the late 90s. These did well in their time. We did a lot of consulting work, but the business model was not great. We hadn't figured out how to kind of keep the business model going at the same time as publishing our open source. But these companies did a lot of great work. One of the things Lineo did that I don't think I mentioned later is we supported the BusyBox project. We actually had the BusyBox maintainer on staff. And so we paid for the first 3 or 4 years, very key years for that project. Lineo was the host for that. Monte Vista did a great job of getting processor vendors to support Linux. TimeSys, their focus was really on real time. So we each kind of took different areas that we focused on, and we made a big difference. One of the things that we did in those companies is we started to forums. We tried to approach in kind of the traditional way you get companies to work together on something is to create a consortium or a forum. And so the Embedded Linux Consortium was the first forum that I had been involved with. That was started by Lineo. It actually included Monte Vista, Red Hat, IBM, and others. And interestingly, it did not focus on technology. It focused on marketing. So we would go to trade shows and we'd just show products running Linux and say, hey, so our job at the Embedded Linux Consortium was to prove to people that Linux was real. It could be used in products. And so it was kind of a marketing organization. We did try to do some standards, but they kind of fell apart. They didn't work out that well. Anyway, in the aftermath of that, I was hired by Sony and a group of Japanese companies, And I have to say, again, these companies were very visionary. It included Toshiba and Hitachi and Fujitsu and NEC and a bunch of others. Um, and they were visionary, saying, look, we should get together and work on the feature set of Linux. Make sure that if we're going to like be serious about using this in our future products, we need to address some of the technical deficiencies. And so that's what we did. We that self was formed, and we actually had 6 technical working groups at the very beginning, and we focused on these were the issues: real time, system size, security, boot time, power management, and then we had a single group that was doing audio, video, and graphics, which was kind of a lot of territory for one group to cover. But anyway, um, and this is one of the first lessons. So the first year of self, this is in 2003, we had these requirements meetings in San Jose, and there was in the meetings we were saying, well, we got to get like work groups, and we got to get the work group chairs and stuff. And it's like, well, who wants to lead the boot time working group? And nobody raised their hand, so I finally raised my hand, and so I became the chair of the boot time working group of the CE Linux Forum. I'll come back to that. So we spent a lot of time making requirements documents and specifying standards. We produced our first technical specification in 2004, and we had a kernel tree that people could use in products. This is the boot time spec. So we gathered requirements and solutions. We collected patches. We had work group meetings. We published our own tree, the CE Linux tree. It was actually based on a vendor tree from Monte Vista. It was the 2.4.20 version of the kernel. And we pre-integrated some of the patches we identified. But we did not have great participation from Linux kernel engineers. So we had some people in the forum that were familiar with Linux development, but we didn't have our degree of technical expertise and our degree of open source knowledge was not great. Anyway, I can remember we made some submissions to the kernel and said, hey, we've got these specs. Are you guys interested in these? And Ted Cho, who's one of the lead developers on Linux, said, why are you making specs? We don't care about your specs. Said, just make the patch, send us the patch, we'll review the patch. Says, encapsulate the requirement or whatever, your feature into a patch, and that the community works on patches. And the other thing that we did is we had a bunch of work group meetings that were started private at first. So we were all discussing kind of amongst ourselves. And those were some of the mistakes. So why did we fail? Well, I'll tell you a couple of reasons. We didn't, I have to be careful here. So some of the things that self did not work out as we'd planned, but some things did. So the things that didn't work out. So first, our initial interaction with upstream was completely wrong. The way we approached them was wrong, and working on specs ahead of implementation. Also, at this time, this was before there were any tools to manage patches out of tree. This was before Git. This was even before, Linus was not even using CVS. He was using patches and tarballs. And this even before Quilt. So it was really hard to maintain this tree. Also, the incentive structure for the members was not right. So a bunch of the big companies that were using Linux, we wanted a shared maintained fork of the kernel. We also had Linux vendors who were members of the forum. They did not want to share that implementation. That's what they sold. That was their business model was kind of wrong at the time also. So they were not incentivized to support that central tree. And then there were processor vendors, and we had a hard time getting processor vendors even paying attention to us. So it was still kind of too early for the processor vendors to be interested in Linux. So basically, we created a hard to maintain fork of Linux, and we didn't have sufficient resources to continually sync with mainline. And one of the problems is the way we had it structured is we treated the source tree as kind of an end goal that people could use. We didn't have processes for upstreaming very good. So I would just want to note that the civil infrastructure platform, I think, learned a lot of lessons from this, and some of the people who are in that project. So they have a completely different setup, and they're doing it the right way. different semantics. So, a couple of things they do is upstream first. They have paid experts maintaining the tree and a bunch of other things. So you can make this type of setup work, but we didn't know enough to do it correctly at the time. So some of the important lessons. Be careful what you volunteer for, because when I raised my hand, I worried that when I raised my hand, I'd be signing up for something that was going to take a long time. And I'm still doing boot time work 22 years later. Okay. So also an important lesson is you lead by implementing things, not by specifying things. The best way in open source is just to do it and show that the code is there. Make sure it works and then contribute it. Also, I learned both in the self context and at Sony. I was Sony's kernel maintainer for a couple of years. Maintaining your own kernel tree is hard. It's hard work. And submitting patches up to the upstream by proxy is also hard. I'll talk about that. And the other thing that was really important was not to treat the open source community as this separate entity. You need to actually work with them early. So parts of the self, so I don't want to be all negative about self because it did accomplish some good stuff. The parts of the model that worked was that we hired existing kernel developers to create technical solutions and to mainline them as part of the contract. So we hired a guy by the name of Matt Makel and paid him to work on the Linux Tiny project. And we got a lot of patches upstream from that. We got boot time patches upstream. We had power management patches that got upstream. We paid the developer of Squash FS to upstream his code. It was out of tree. We actually just had a contract where we just paid him straight up to spend a couple of months putting that upstream. And so each year we would put out contracts for bid, and the goal was always that the result needed to go upstream. And that was a good thing. That was a good transition for us. The other thing that I think was really useful and helpful was we turned our technical meetings into open conferences. So our public work group meetings were private at first, but then we turned them into the embedded Linux conference. And our goal was not to make money with conferences. That's different from a lot of other conference. A lot of times the organizer of a conference is there to make money on it. Our goal was not. Our goal was to disseminate information. And so, a lot of people don't want to. Well, anyway, we were the first conference that I'm aware of, at least in the technical space, where we took videos of every talk and we published the slides and the videos to the whole event. This was started by Free Electrons, but our goal was disseminating knowledge and building a community. And I think we did a good job of that. And another thing that we did, of course, was we started regional meetups, including the Japan Technical Jamboree, which we're at now. What we also did was not just focus on our own embedded ecosystem. We attended other Linux events, and we tried to make other upstream developers aware of our requirements. So we went to places like Ottawa Linux Symposium and LinuxCon Japan, and we did outreach to non-embedded events, and we also invited non-embedded engineers to our events so that we could exchange information between the embedded ecosystem and the wider Linux ecosystem. I kind of refer to this as reverse marketing. So we were marketing not to users. We weren't selling Linux to non-Linux people. We were selling embedded to non-embedded people. So we were teaching embedded requirements to developers in other fields, and we had success starting to build an embedded community. This is one year we decided to have a BOF, but we hadn't decided ahead of time, so we just made a poster and put it on a wall and invited people to come over to a hotel room where we talked to them about embedded requirements. It was very ad hoc back then. And there was at one of these events, there was a key lesson that I learned. I had dinner with one of the kernel developers at Ottawa Linux Symposium. You go out for dinner after the things. And I was talking to him about my frustrations getting patches accepted upstream. And I kept saying, here we are, we're working on, as an industry, we're working on this and we're working on that, and we keep pushing patches to you guys and you won't take them. And he stopped me and he said, wait, your language here is all wrong. He says, this is Andy Clean. He said, you have the wrong mindset. There's no we do this and you do that. He says, it's all of us. All of us are part of the open source community. And so you're just as much a part of the community as anyone else. And so you really need to think in terms of us and we, and it's, you know, it's not a separate group. And so that really had an impact on me. You really should treat all community developers as partners, as someone on your team. And I mean, you know, anyway, you're not inviting them to your weekly staff meetings, but in terms of the technical strategy or technical development, communicate with them as openly as you would, you know, members of your team. Well, when you can. Okay, so the other thing that happened was we saw a shift in the industry, the way that the consortiums, instead of these general consortiums, we saw more specific consortiums that were at targeted development areas. So the Linux Foundation started creating projects, and one of the first, one, they kind of absorbed the CE Linux Forum into them as a project around embedded Linux, but they also started the Yocto project. They started automotive grade Linux, drone code, the civil infrastructure platform, and they're currently incubating the space grade Linux. That I'm hopeful that will actually get created this year. So what we saw is, instead of a general organization that's handling all of embedded Linux, because it's kind of too big of a territory, you saw these vertical groups organized around specific problem spaces or market spaces. So, you know, automotive, and that's been very, very successful. Drone code is very successful. AGL is very successful. I think CIP has been really good at addressing their requirements. And so I think that is a really good way forward. What that does is it helps concentrate the open source efforts around that particular ecosystem. So the growth to world domination. How did we do it? Well, there was the slow technical maturation, right? So over time, self and the community, we fixed lots of bugs. We did a lot of early work on technical problem areas. So we worked on real time. We worked on size, boot up time, power management, those original problem areas. But we also did other things to address the SoC and the processor support. So we added device tree. So one of the problems outside of the Intel space was there's not a standardized BIOS for managing hardware. And so device tree was added to the kernel. Linaro and other companies that were focused on specific processor markets came up and started helping with that SoC support. Another thing is the tools became much better and easily available. It used to be a very, very difficult process to get a cross compiler, and now it's not. Also, the build systems matured. And again, there are lots of feedback loops and network effects from all of this. So the increased adoption of Linux increasingly led to other people kind of joining on. So processors who originally ignored Linux now started writing the processor port themselves. So in the very early days, I can remember when all of the ARM support was written by one guy, Russell King, okay? And he was not an ARM employee at the time. He was just a volunteer writing stuff from spec sheets. But that's not how anything happens today. Nowadays, hardware vendors and processor vendors, they're writing the drivers themselves. And it got to the point where Linux is so popular as an embedded OS that if your processor is not supported by Linux, people are not going to buy your processor. And it turns out money is a great incentive for people to start adopting this stuff. And then as more embedded developers started using Linux, more and more things got fixed. It was just a nice virtuous cycle. And I can remember when Google came, Google appeared the first time at a conference, I think can't remember what year it was, but 2012 maybe. But they showed up and they had all these patches because they had done Android, and they had a bunch of weird stuff. And it probably took about 5 or 6 years before we were able to figure out how to factor in all of Google stuff and get them up stuff. They had this thing called wake locks that was really strange, but did power management. But anyway, and the thing about it is, Google came in and they became a contributor, and things improved for everyone. It was the open source effects doing it. Another thing that happened, which was really key, was Moore's law. Well, Moore's law is the law, but the effect it had. So it fixed a lot of our problems for us. So the basic idea is that advances in memory size and processor speed took care of some issues. So Moore's law, I'm sure you're aware, is this idea. It's not a law, it's just an observation that transistor counts in microprocessors double about every 2 years. And maybe we'll hit a wall, but they just keep doing it. It's amazing. And so what that meant was that the marginal cost of a transistor goes down, right? If you can fit double the transistors on a die, then theoretically they cost half or a quarter a piece. So you can put more transistors on the die, add more gates, and because things are closer together and there were some other technology developments, you could run at higher clock rates. And so that meant that for less cost, you could actually have a processor that cost you less money, that ran faster, that had more capabilities. You had increased memory. So it turned out that size, we just plain stopped working on the Linux Tiny project because the smallest DRAM you could get was 32 meg. And it's like, okay, well, why are we putting this effort into it? Well, that's true if the software stayed the same size, which it didn't. Okay, I'll talk more about that later. But you could also put software functions in hardware for better performance. You could add more logic for controlling the gates, controlling voltage and frequencies. So you had hardware support for power management. And this is a little controversial because it's not quite true, but you could hit your real-time deadlines more easily. So if you had a real-time deadline that was real in absolute terms, like a 1 millisecond, if you had a gigahertz processor, you were hitting that much more easily than if you had a megahertz processor. It turns out for real-time, determinism is more important than CPU frequency, but CPU frequency helps. So Moore's law was great. It allowed us to start wasting hardware like crazy. We could bloat up the kernel and not worry at all. For example, in 2004, I was working on Sony's digital camera team, and they gave me a budget of 10 megabytes for the Linux kernel and distribution. It was brutal. It was, and it took a lot of work with Linux Tiny and other patches. And I used to joke with people at the time. It's like, oh, you work for Sony. What do you do? I work on the digital cameras. It's like, oh, well, what did you work on? I worked on all the code that's not there. The code that I removed was my add-on to the project. But in 2026, okay, so a modern camera has a budget in the gigabytes of RAM, and Linux just got bigger over time. So Linux got bigger, but memory got bigger faster. And so the Moore's law solved a bunch of these technical problems that we had, but it also created some problems. And so, like I said, Linux Tiny is not as important as it used to be, at least for that product category. Another difficulty that we had at CE Linux Forum was we had a real hard time contributing stuff upstream. And one of the reasons that we failed to sustain our source tree effort was that our contribution model was kind of flawed. Our original plan was to have members contribute upstream or to submit patches on behalf of our members. So our members would bring a patch, we put it into our tree, we'd do some testing, write up a spec for it, and then try to submit it upstream. But it didn't work. And one of the reasons it didn't work was, there were two reasons. One of the reasons the members came to us is because they didn't have open source expertise. So they were hoping that we would do the upstreaming. So they didn't do the upstreaming themselves. And then the Linux vendor members, they didn't want to contribute. They didn't want to give the fixes to us. Some of them did upstream work, but they really were trying to keep their tree to themselves. And then the other thing was that the self-staff were not subject matter experts. So we'd get a patch that had to do with USB or with a file system or something. And if you weren't a file system expert, it's really, really tough to represent that patch to the community, right? You just don't have the expertise. So proxy contributions are really, really hard. That didn't keep me from trying again. Let me give another example of this. So when I went to Sony Mobile, the Xperia phone had an Android Sony Linux kernel tree that we got from our supplier, which was Qualcomm. It had 600 patches by Google, which is not that bad, manageable. 2,000 patches from Sony. Okay, that's a lot. 25,000 patches from Qualcomm. It's like, oh my gosh. It's like practically not even, it's almost as many lines of code in patches as there were in Linux. And moving from one release to the next, when we switched kernel versions, it was at least a 6-month effort because we had to forward port all our patches. We had to go back and recertify a bunch of stuff. And so this is what created that 3-year version gap that I talked about. And it was just a huge hassle. Someone had to port those 25,000 patches, all had to be ported every time they did a kernel release. Sony and Google were not incentivized to do that porting. Qualcomm was not very enlightened. They were not doing open source very well. So Sony came up with a solution, or at least some people at Sony came up with a solution. Let's do the Open Devices project. Our goal to close that version gap was to support the latest upstream kernel on our mobile phones. And the way we did that was we were going to, our goal was to create a baseline for contributing phone patches upstream. So we wanted to make it easier for both us and Qualcomm to submit patches upstream by getting the latest kernel source tree operating on our phone. Also, we thought, well, we can open it to the public. We can let the public contribute patches as well. We'll get third parties to improve the phone. And this should help reduce our own internal effort every time we have one of these release changes. So our method for that was we got to get the top of tree running on the phone, even if it's not fully feature complete. And what we did was we upstreamed as many items as we could to the kernel and from Android open source projects. So we were contributing Qualcomm patches, we were contributing Google patches, we were contributing Sony patches, and we were doing this on behalf of Qualcomm, even though they weren't. So this was not Sony's hardware. The fact that we convinced management to let us do this was amazing. You may be wondering, did it work? No, it did not work. Because proxy contributions are hard. It's just too hard. We made some progress. So actually, it was pretty amazing. There were Sony phones that where you could go to our Open Devices website, download the latest kernel, the top of tree kernel, which I think at the time was 3.4, and you could install the latest kernel on your phone. A bunch of stuff wouldn't run, I think notoriously, but it was the latest kernel running on the hardware, and there was a lot of work that went into that. So we actually demonstrated top of tree kernel on our hardware, and we used that as a platform to contribute more patches. So that part of the project worked. And we did. We got outside contributors. There were non-Sony employees who were sending us patches that we could apply to our Sony phones. That's like the magic of open source, is having other people do work on your platform. But overall, the project was a failure. There were a couple of reasons. You could probably guess them. There were not enough resources. The technical debt was just too big. And we didn't have sufficient documentation and sufficient expertise. There was lots of dependencies. Qualcomm's chips, they have all these other processors on them, and there was missing features, and so we couldn't really build a solid base. Only the most advanced and aggressive hobbyists would download this, right? It wasn't kind of normal people. But there was one interesting outcome of all this. I'll just do this as an aside. Bjorn Anderson was the head of this project. He went on to Linaro on the Qualcomm landing team, and then eventually ended up at Qualcomm. And now he leads all the efforts at Qualcomm to mainline stuff. And there was a presentation in May from the Qualcomm team about how well they're doing with upstreaming. So, and part of it is because Bjorn has this previous experience. So eventually things worked out. But here's some of the lessons I learned about proxy contributions. We didn't have enough internal information. We had access to data sheets, and Sony, as a partner with Qualcomm, we had more information than a lot of other customers, but it still wasn't enough because we weren't the engineering team themselves. There was one bug I worked on uh, that took a super long time because it turned out that there was an undocumented register that could flip the SPI on and off. It's like, oh my gosh, it took forever to find that. This wasn't a high enough priority for Sony. It's really best if subject matter experts make the contributions. I do believe that upstreaming saves effort, and Qualcomm uh, had at the time they had over 600 engineers working on Linux, and I think with upstreaming they could have had way less. I think they have way less than that now. I think they're doing a lot of their upstreaming with a team of like 10 guys. Um, so I have a whole presentation on this if you want to see the gory details, a lot more detail about it. But so that's my lesson about proxy contributions. So why I want to answer the question next. Why is embedded Linux community development so hard? What makes embedded Linux harder than regular Linux? Because it is hard. So I'm going to answer that by talking about the embedded open source contradiction. So this is it in its very, very simple form. I'm going to get into details a little bit, but basically when you're working on an embedded product, you're working on a specialized stack, a specialized solution, right? It's something that does one thing and does it well. So like if you're working on a camera, it does the camera software and controls all the things in that. But as I said in my previous talk, open source prefers generalized solutions. So there's a contradiction there. It's difficult to get the benefits of open source for embedded projects because of that dedicated functionality. So when I go onto the mailing list, the chance that I'm going to run into like I'm working on a Sony camera, the chance that I'm going to run into and start communicating with, someone else who happens to be working on a camera stack is pretty low, right? They might be using Linux, and we're both interested in things like the scheduler or memory management. But the higher you get, like into the drivers, no, the Olympus guys are not, they don't care about the Sony's camera sensor driver, and I don't care about their sensor driver. So as your products specialize, right, you don't get the open source effects. At any particular moment when you're out in the community, other developers are not focused on the same issues as you. And one of the things that I realized is that a lot of work in embedded Linux is what I call re-specialization. So one of the conferences I went to at ELC Europe in 2010, I had this epiphany. I had a vision open up to me uh, by a talk that I watched. It was by Andrew Murray, and he was talking about boot time and how basically boot time was was all the stuff that people had done to generalize Linux. They were ripping it out to make the system boot faster. And so you take something that's generalized and you re-specialize it. So, and it's custom. It only works on your hardware. And so you can't share that with other people. Um, and so this was true of boot time, but it's also true of other things like system size and power management. A lot of the solutions in the embedded space are solutions that are special case for individual hardware or for individual product areas. Um, so this is his talk, and this totally changed my thinking about boot time. That boot time is a re-specialization problem. You have to remove all the gunk that it has accumulated over the years and make it specific again. And he gave a whole bunch of really great techniques, but the philosophy and the idea is really more important than those individual techniques. So general software is expensive to write. It costs more to write because you have to deal with everybody's cases at the same time. But it's the only way you can build a community. you have to have generalized software. You have to address the needs of multiple parties to get those open source effects. And the parties need to work together on that. But if you look at it, kind of going back, I'm going to have a Lego analogy coming up here, but generalized software does not perform as well. It's bigger, it's slower, it uses memory and CPU cycles because it's doing all this stuff that your product probably doesn't need. It doesn't matter for your product. So there's where the tension is. You have this tension between generalization and specialization. Um, so the other thing about general purpose software is general purpose software has to deal with dynamic environments, right? So if you're talking about Linux on a mobile phone or a desktop or a server, you don't know in advance what the workload is you're going to run. So it has to operate with all these contingencies. It has to manage a much more complex environment and be much more reliable. Embedded devices have a dedicated functionality. A lot of times, so for instance, for a router, the application stack is really, really limited. It's very, very constrained on the inputs, the outputs, and the state. And so you don't have to handle cases ahead of time. You don't have to think, oh, what if, like for a router, you don't, well, router, you don't have to wonder like what module am I going to have to load if the user plugs a USB stick in. You'll only support maybe USB mass storage and that's it. But for a PC, if you're running a desktop version of Linux, you have to support like every possible PC device they could plug in to USB. So it's quite a different thing. So here's where Moore's law and this contradiction intersect. Moore's law let us move into this from this special purpose world to a general operating system. So over the course of time, because of Moore's law, we were able to go from like bare metal and VxWorks, PSOS, all these RTOSes, and move to a general purpose operating system because now the hardware was fast enough and it was big enough to handle that. So we have all these things that we can waste stuff. So the same thing happened with hardware, by the way. In the early days, hardware was custom. It was specific. We started with microcontrollers, very limited functionality. But modern hardware, if you look at an SoC, it has tons of features on it that may be completely unused when the hardware is used in a particular application. So just as a simple example, let's say I want to use a Raspberry Pi as a router in my home. That's a common thing. There's a product called Pi-hole which does DNS routing, right? The Raspberry Pi has HDMI on it. Do I need that? No. Okay, not for my little router. But I'm still going to do it. Raspberry Pi is still the cheapest thing I can get to make into a router for my house. So I've got all this junk on a Raspberry Pi. I've got the audio, I've got the HDMI, I've got all kinds of stuff that I'm not using at all. And the same thing that happens with hardware happens with software. And we're wasting it all, right? We're not even using it. The cheapest RAM you can get is 32 meg. It turns out, I was talking to the semiconductor people a while ago. This blew my mind. It costs the exact same to produce a chip with 8 cores as it does with 3 cores. Okay, that's a weird analogy, but that happened to be a particular Sony semiconductor. It didn't cost them any more to have more cores on it. So they just threw some more on. Economies of scale means that you can have fewer general purpose designs and do those in greater volume, and that's cheaper than custom silicon chips. And so you see these chips that are over provisioned, right? They have too much stuff on them. Not too much, just the stuff you don't need. Same thing happens in software. So what happens if we want to respecialize though? Okay, so getting back to this idea, we want to take this big general purpose thing and we want to get it to boot fast, or we want it to fit in a small amount of memory. Can we remove size, reduce boot time, take drivers out? Well, you can do that. You can make Linux slimmer. There's lots of config items, but there's a problem with that. And here's my second Lego analogy. So Linux is actually pretty wasteful for doing embedded work. It's generalized and has lots of items that you're not going to use. The same as with those SoCs that have all those gates that you're not going to use. It's kind of like this Lego crane truck, right? So here's a truck. It's a neat truck. It does a lot of stuff, and it has a lot of Lego parts in it. You could take the parts out of this and turn it into something smaller. So yeah, look at all that cool stuff. So what happens? Can I do that? Can I take Linux and turn it into, like, let's say I just want to make a little router. Okay, in this case, the analogy is it's a small car. Look how cute that is. It'll run fast. Well, what happens is the pieces don't actually come apart that easily, right? There's dependencies between the pieces. When you try to break it apart, you end up with what I call a Frankenstein car. It's like, yeah, well, that wasn't the router I'd hoped for. I was hoping for a nice little thing. But it turns out the Wi-Fi stack needs a radio driver, a network stack, crypto, libraries, the scheduler. So there's all these dependencies between modules that make it so that trimming Linux down to size is very difficult. What you really want, to extend the analogy way past where I should, is a completely custom car, right? So this car is great. This has exactly the pieces I need and no more. It doesn't have any extra nubs, doesn't have anything sticking out. It's the most fit for my purpose. But this is like writing the full software from scratch, right? So I designed every last little detail of this car. I created an injection mold, and it's exactly what I need. But it's very expensive unless you go up to huge volume, right? It's very costly to set up the manufacturing, just as it would be super costly to do bare metal development of an operating system stack, Wi-Fi stack, all from scratch. And here's the problem. If I do this approach where I custom make it, I get no open source effects because no one else is going to help me with this, support this car, maintain this car. Okay. And so that's a dead end. So we're stuck. The Lego mini car would be great. If we could get to here with Linux, that would be awesome. This is the perfect solution, but it's too costly. This is in reality what we end up with. So this is my comparison. Bare metal, using an RTOS or reduced Linux, that's what we want. But this is what we get in reality. Okay, so the problem is what I call subtractive engineering. And this is what I did on Sony cameras. We try to get to that mini car by taking things out. And it turns out that in some cases, taking stuff out is harder than putting stuff in. It's hard to remove things. And in particular, well, one of the reasons is there's unstated dependencies, right? You don't know about the dependencies between modules. If you've ever tried to reduce glibc, like try to reduce the size of print K in glibc, like remove one of the format specifiers. You won't get anywhere on size because there's just too many other dependencies. So you can do some things, right? You can do things with config trimming. And Linux has over 21,000 config options, but people don't turn them off because they're scared, because they don't know what's going to break. And you either have to do a whole lot of testing or you have to really understand the dependencies. I did subtractive engineering for digital still cameras. You can do it. It's possible to do, but it's hard. It takes longer than you think. And again, once you've done your trimming, you lose the open source effects. If you trim Linux too much, you lose those effects because no one has tested Linux in that configuration. So you lose community and there's no longer as many minds, but there is hope. Okay, so now I'm swinging you all around on the spectrum of hope. So these days you have other options. Okay, and I can't believe I'm saying this, but if you really need to go small, you can go to Zephyr or you can go to NutX, and these are RTOSes, but they were developed in a modern way with open source communities and additive engineering in mind, right? So you can jump off the Linux ship, but you still have the benefit of open source because these operating systems were developed to complement Linux. Often you will see dual designs where you'll see Linux and one of these other operating systems on the same hardware, on the same processor, on different, same chip, different processors. But with these, you can do additive engineering instead of subtractive. And the other ray of hope uh, is you can use a minimal Linux system that's already someone else has already created, right? So there actually is something called PokeTiny that is still in the Octo project. That's a maintained project to do a small Linux system. And I was absolutely shocked when I saw that we had not one but two talks at ELC this year in May about small systems. We haven't had a talk on small systems for a couple of years, but the Jim Huang is a developer. He's actually a university professor in China. They had optimized Linux to fit in microcontrollers with 1 meg of RAM. It's like, okay, that's awesome. Someone's keeping the dream alive. And then the other person was Rob Landley. Rob Landley has he has the smallest distribution you can possibly imagine. I think it's under 400K. And he can build it from scratch. Anyway, so there is work in Linux to do this. And my recommendation, you can choose one of those three routes to deal with this contradiction. The best thing, of course, is to stay where you can continue to use those open source effects. I presented this next slide a couple of years ago, and I still want to see it happen. I believe it's possible to run Linux on a serial box. You can now get a processor that runs Linux that costs $1. I have talked to people in the serial box industry, and they say that the cost threshold for putting something on the box, or a toy in the box, or graphics or something, is $1.50. So you'd have to get the display and the input in under 50 cents, but we're getting close. Why would you do this? I have no idea. But I think that if there was a box of cereal that was on the shelf that your kids could play Minecraft on, your kids might ask you to buy that box. And so I think there's actually a business case for cereal that runs an operating system. And I would love it for it to be Linux. I think we're actually pretty close to it. When I originally presented this in 2012, and it was a pipe dream, too far away, I think we're actually have made a lot of progress, and we could see this happen sometime in the future. I don't know if anyone will do this. This is just my personal dream. I think it'd be really cool. Linux has shipped actually in magazines, and there was a really interesting case where the commemorative edition of Doom came in a box that ran Doom. So we're seeing stuff like this start to happen. Anyway, but that's kind of the embedded contribution. So where are we now after talking about all this stuff? Well, Linux is now the dominant operating system in embedded markets. Recent surveys show that Linux is 51% market share. That's across the board. So that includes IoT stuff and everything else. We've taken over from the previous incumbent, which was FreeRTOS. We have tons of tools and support that are available for embedded Linux. No problem getting across compiler environment. We have build environments. We have libraries that are specific for embedded, BusyBox, Toybox, vendor-specific SDKs. Hardware is available. It's cheap. You can get a dev board for under $100. I recently started some work on space-grade Linux. I had to buy a RISC-V board that was FPGA based for that, for obscure technical reasons. But it was $145 to get involved with Linux. You can get an all-winner board that runs Linux in $1 in volume, which is pretty that's pretty crazy. Let me go through the technical issues scorecard. How are we doing on solving these problems? Well, real time. Preempt RT was mainlined a couple of years ago. Real time is actually in pretty good shape. You could always get better. System size. again, things grew. The kernel is much bigger than it was 20 years ago, but it is possible to trim stuff down. And if you're willing to go no MMU, you can get things well under 2 megabytes. So it's okay. In terms of Sony's products for TVs, camcorders, set-top boxes, robots, uh, we don't even care about the size anymore. Well, I don't say we don't care about the size anymore, but it's not an issue. We're not trying to squeeze things in the kernel like we used to. In terms of security, okay, you're always going to have security issues. More issues are appearing constantly, but they are addressed. We have pretty good security practices. We have Rust in the kernel that is starting to make inroads, and as more of the kernel, Rust solves particular types of security issues, so that's good. Boot time, okay. Here, after 20 years of working on this, we're still not done. Android still takes about 30 seconds to cold boot. If you roll up your sleeves and work hard, you can get a system to boot in about 2 seconds, which is just enough for regulatory compliance on automobiles. But hardware speed, it turns out, has not outpaced the rate of bloat in boot. Most of that is actually due, well, I won't get into details. Power management is great. Audio, video, graphics, lots of options. SoC support is really, really great. Okay, I used to do, like I said, the status of embedded Linux. After 20 years, this is my first year. I'm not doing that talk. My first time at a Japan Jamboree, I'm not doing that talk. I have passed the baton to a guy by the name of Walt Miner. He gave a good presentation at ELC in May. So if you are interested in the status of embedded Linux, you can check that out. And there'll be another instance in October. There'll be another State of Embedded Linux talk. The bottom line is that the resources to become an embedded Linux developer are all available. We have tool chains, cheap hardware, tutorials, presentations. What about this AI thing? Okay, AI is kind of a looming thing. Is this just another tool, or is this actually a fundamental paradigm shift? I don't know. I couldn't tell you. AI is putting stress on open source in kind of unexpected ways. I don't know if you've noticed, but in order to go to the lore.kernel.org website and look at issues, you now have to pass a human filter. And that a lot of projects have had to put that type of barrier up. So the training data for AI is being scraped and sometimes unscrupulously. And AI, because of it's so easy to generate code, it's putting a lot of stress on maintainers. They're getting overwhelmed, which is bad. But at the same time, there are maintainers that are using AI, and there's an automated system for the kernel that does AI. And so AI is both helping and hindering open source. Linus, in his last talk that I heard, when he was talking about AI, he says, well, it's just like any other tool. It's like a compiler. It makes people more efficient. You can produce either good code or bad code with it. But in his view, it's a tool. And I think I was talking about this actually during the break. I think there'll be a transition. Oh, and the question we had last session. I think there'll be a transition cost as we move to AI. Personally, I'm kind of wary of AI generated code. I do not use it to generate code. But there's more and more AI stuff appearing in the Linux kernel all the time. So we'll see what the future holds. Could be great. Compilers totally changed how people programmed, made it a lot faster to develop code, and AI could do the same. So where are we now in summary? Wow, things are going great. This is the golden age of embedded Linux. So just to recap my lessons learned. In open source, you lead by implementing things, not by specifying things. You should really treat the community as a partner. Don't treat the community as a separate entity. You get in the mindset that you're a team, that you're a part of the community. Moore's Law has solved a lot of problems, but we always want to optimize more, don't we? And then open source is a contradiction. the natural tendency is to fragment and not work together. And embedded makes that even harder because we're on different projects and different technology stacks. But you can do conscious community building. That can help. And things are always changing. So, enjoy the ride. I have a couple of resources that I'll just skip over here. I'm going to do a PDF for this. And this, when I went back and reviewed, this is now the 90th Jamboree that we've done. We started in 2004? Oh, anyway. So we have a lot of Jamborees. There's a lot of technical content that is available, and surprisingly, a lot of it is still really valuable. My conclusion from all of this, everyone has an opportunity that you can play a role in contributing to open source. There are lots of challenges left. When I talk to people, new developers especially, I say Linux is what the military term is, it's a target-rich environment. There's a lot of stuff remaining to do. It's a good life. It's lots of fun. I am retiring from full-time employment in August, but I think I'll probably still be around for a little while, and I look forward to seeing your contributions in the future. One last thought, a final thought. I have really, really enjoyed interacting with the culture and the community in Japan. I've now been coming to Japan since about 2000. I have many wonderful memories of my times here and my interactions with you and with the developers. Ultimately, Japan has been a big part of my life. I have spent over 1 year of my life at the Shinagawa Prince Hotel. And I really think they ought to name a room after me or something. I get a memorial room. Anyway, thank you for being my friends over the years. And I really appreciate your time and your friendship. We've had some really great times together. Some of us look a lot younger in some of these pictures than we do now. But anyway, thank you for coming. And again, thank you for being my friend for all these years. So.
ちょっとそうですね。質問何かありますか Do you have any question or comment or something else to him? Message?
Thank you very much for your great talk. And I have one question about we and you communication between with open source community. I've heard a similar story from Ueda-san, but it is the same. Is that communication among including Ueda-san with that exact specific discussion?
Sorry, can you ask it again?
I've heard similar story from Ueda-san. Ueda-san mentioned something like from open source community. Ueda-san had been asked to use we.
Oh, yeah. Well, I know that my story with the OLS developer was with Andy Clean. I don't know if Ueda-san borrowed my story or if I borrowed his. But yeah, it's the same thing. I think that is important.
Okay, thank you.
どなたか他におられますか
Thank you so much. And you spent more than 20 years for good time.
Yes.
So, so now you're most probably tried. So what kind of topic you want to spend next 20 years?
Oh, so yeah, people have asked me sorry. People have asked me what I want to do in retirement. So I have a lot of ideas. So, but there's a couple. I want to build some robots. I haven't really got into robotics. I haven't had time to play around with AI seriously yet. So there's AI, and then I have. This may surprise you, but I have non-Linux things I want to do too. So I have a couple of projects in mind. Uh, I'll let you know. One of the things I want to build, just because I have a big lawn, is I want to build a weeding robot, and so, and I was. This is a funny story. So I was talking at embedded Linux conference. I was talking to a company that makes industrial agricultural equipment, and they asked me what I wanted to do in retirement, and I said, "Oh yeah, I want to do like a weeding robot and get like some AI and vision, and some spray pesticide or herbicide anyway." And I could tell they all looked at each other like, "Hey, we're doing that." So I thought that was funny. Um, so I have some technical projects to do, and also full disclosure, uh, I'll probably be hanging around a little bit, at least part time, doing some consulting for Sony. So I won't completely disappear. You can still reach me at my Sony address. At least I think you will be able to. So
Alright. Yeah, that's very interesting. So good luck. Thank you very much.
yeah.
Thank you, Tim. So you talk about the definition of the embedded use case is really inspiring for me.
Yeah.
I mean, yeah, it's kind of very specific one. But um, recently, I feel like the things are kind of changing. I mean, we need much more generic or um, prepare for future updates or that kind of changes occurring in our industry.
Yeah.
And so that this is just a comment, but that inspired me a lot. And so we embedded Linux community should consider something new or what we should do, what we should address for future or next couple of years.
Yeah.
Yeah.
Yeah. I think so. So part of my embedded contribution thing, right? I said that Moore's law has solved problems. So I think the set of products, so that can run Linux easily, is different now than it was 20 years ago. 20 years ago, it was hard to run on camera. It was hard to run on a TV. And because of Moore's law, it made it easier for those. There are still domains, however, where you really need like a sensor that can run a year on a coin cell. And so you're more concerned with like maybe a static RAM or even a MRAM type of solution that draws no power whatsoever while it's not processing. And so there are realms, especially in Internet of Things, for these very aggressive low end things. So I think the the category of products where Linux is challenging has changed, but there are still plenty of places where Linux is challenging and where we can do good technical work to solve problems. So
You mentioned about the Android boot time taking around 30 seconds. It just reminded me of this Zygote trick that it does. Are you familiar with that?
I'm not.
So apparently, once the Android system is completely up and running, no process ever issues the execv system call, even for forking, for creating new processes.
Oh.
So most Android applications, they're JVM based. So what happens is the Android, the core system, first creates this zygote process, which has the JVM completely initialized. So when a new application needs to be launched, that zygote process just gets a request to fork off, and then it can read the JVM bytecode and start executing. So it never calls the exec-v system call. It just keeps forking all the time.
That's really interesting.
Yeah.
So the other thing that Android, right? So it turns out that Android rarely cold boots. So that figure I gave was the cold boot time, but that's only when you do like even well, it depends on your manufacturer, but even when you're doing a power off, a lot of times you're just doing a hibernate. And so there's turns out that you know, especially like right now, my phone's running. It's just in a low power state, even though, well, it came on when I did that, but anyway, yeah, even when it looks like this, it's not off. And so they cheat. Oh, it keeps changing on me. So there are other tricks that people have done, right? So what's the snapshot boot was one of the famous ones that where and it's yeah. So there's interesting stuff going on all the time, and yeah, as long as people are happy with their products, I guess, you know, we're happy to give them the solution.
Yeah. I have another question. So
Yeah.
another thing I feel in the embedded domain is that people may be hesitant to upgrade to newer versions, which means products end up stuck on older versions, and then they need to be maintained for years. So what has been your experience in this regard, and what's your perspective?
Yeah, product maintenance life cycles is a tough issue with Linux. And as far as I can tell, CIP is the only one that's taking it seriously. So they're supporting Linux. What's the current? Is it 10 years, or do you guys go longer than that? 10 years. Well, and we haven't hit the wall yet. At some point we're going to. At some point we're going to discover that there's like a train system running Linux 2.6, right? And there'll be some horrendous security bug that no one has an answer to. I think in terms of like in the consumer space, right? We want our product. Well, it's a long story, but yeah, we want our consumers to have nice product experiences for a good amount of time, and often that amount of time is longer than the long-term support offered by the community. I don't think we've solved that problem, and so I don't know if I have a good answer for you. Usually, like I want my Sony TV to last at least 10 years, and that's way beyond the LTS on. So I don't know what Sony does. You can always turn off networking, I suppose.
Okay, thank you.
Yeah.
Thank you, Tim-san. I have a question about the proxy contribution. So I understand that proxy contribution is not working, but from your previous talk, so the only option is that make them understand the good point of the upstreaming.
That's right. So I have to be careful. So I talked in kind of absolute terms. It's not impossible to do a proxy contribution. It's difficult though. And so yeah, the best case scenario is when the original engineers, either the ones fixing the bugs or the ones designing the software in the first place, are available to send the patches upstream. And for that, you need to get buy-off from management. I actually think things have gotten better in terms of corporate understanding of open source and the value of putting resources on it. And some companies do better than others, but it's a continual fight. And in fact, one of the I'll use an analogy here. There's always a new crop of executives that needs to be taught the value of open source. And I think it would be, well, I don't know. My personal opinion is it would be, I wish that the Linux Foundation does a lot of kind of open source promotional materials that are targeted at the executive suite. But I think they could do a better job of, in the embedded space, with like case studies and stuff, presenting the value proposition, so that engineers could justify it up their management chains. So I don't know. It is a real problem, and one that we've been dealing with for years. But it has gotten better. I mean, you see companies. I mean, yeah, I don't want to pick on any one company, but like even MediaTek's upstreaming their stuff these days, so which is really good. They used to be really terrible. Qualcomm used to be terrible, and they're good now. And so, and I just talked to a group this week inside Sony that is going to do their first patch upstream for a particular technology area. I'm not going to give any details, but particular technology area that this is the first time that business unit has really done something this major, that they're going to be working with the kernel upstream. So, it keeps getting better and better. So.
I think also the story of the person from the Sony to the Linaro to the Qualcomm also helpful for us, encouraging now the Qualcomm and Google is providing the long-term Android support, so the situation is changing.
Yeah.
Yeah. Thank you very much.
Yeah.
Okay. Thank you for the presentation, team. I'm the general manager of the system software development in Sony, and I think we haven't talked that much directly, but I have heard lots of things from my colleagues sitting over there, and especially from the Kazumi-san sitting beside me. And I would say thank you for all the activities you have done for the embedded Linux, and also for especially for the Sony's consumer embedded devices development. And I think I'm one of the person who get the most out of your contributions. and thanks for all the activities that we have released many Linux products, not just for the embedded devices, but for robotics and some for the semiconductors. And I think hopefully that will be expanding more in the Sony areas also. Yeah. And in one question to you is that what is your next expectation for the Sony team to do for the open source?
Wow, I don't. I'm retiring.
I think you're the part of it also for a little bit more.
No, I think Sony's doing better and better. So, not to turn this into a Sony meeting, but I mean, the fact that Sony is expanding the number of business units that have official OSPOs is really good. So, because each business unit kind of has its own challenges when it comes to open source, and I just like to see that increase. I think there continue to be opportunities for Sony to utilize open source to do more in participating with open source, but it's really heavily dependent on the particular business unit and what they're what section of the open source market they're in. I don't know. What do I want to see next? I don't know. Just continued engagement.
Thank you.
I have really appreciated my career at Sony, and one of the things I think is really interesting. I didn't mention this in the talk, but it's another lesson I learned, is that if the open source, if you're successful at open source, you actually do things that become invisible to the company. So if you're successful at getting patches contributed upstream, so like I used to manage a kernel tree for Sony that had about 2,000 Sony patches in it. And there was a certain amount of effort that was involved whenever we did a kernel version change. If I was successful at getting, say, half of those pushed upstream, then there's only 1,000 patches. And the idea was that could then cut the release, the turnover rate, switching kernel versions from like maybe 8 weeks to 4 weeks. But it's not something that anyone would notice besides the person who's like directly involved in it, right? So a lot of open source work is the essence of open source is, this is the cynical view, is getting other people to do your job for you. And that's a kind of a bad way to put it, but it's like, it's leveraging, it's collaborating. And when you get more people involved and when you're sharing that cost with non-differentiating software, then the cost disappears, but it doesn't show up on anybody's engineering tracking sheets, right? You don't realize, it's like Sony used to invest a lot of money in the web browser, and we don't invest hardly anything in the web browser. Those costs just go away. So when open source people are successful, it's you have to kind of continually remind management, well, that only happened because we were able to do these processes behind the scenes. So in a way, open source work is kind of invisible to the company. And so it would be nice if there were kind of more formal ways throughout the industry, not just within Sony, to identify those efficiencies that are created and teach that to upper management. So anyway, I don't know. I'm just rambling now. Sorry.
Thank you very much.
大丈夫ですかね。じゃあ、会をクローズしたいと思います。もう一度大きな拍手をお願いできればと思います。So we'd like to bring this event to close, and finally, so we'd like to present a gift to say a big thank you. So Munagata-san, could you please present with your comment?
So I take this role as a proxy of the Ueda-san because I work closely with him. And I want to say the big appreciation for you because you educated a lot of people. And until today, so your kernel summary is much better than AI, of course. But still very much better than kernel newbies and the AWNet because you are adding your own comment and it guides them to how to use that. And I'm very happy to see that you still have strong motivation to the super tiny stuff. Because if you simply run the Linux on the Raspberry Pi, no more special technique needs, just boot. But you're still chasing the very tiny stuff. So please keep working on that. So thank you very much. So this is our appreciation for you. Maybe this time is right for you. Thank you.
ご参加いただきありがとうございました。これ、会をクローズしたいと思います。